Welcome you all for this structural analysis course. So this is a CDT 12 week 4 CD lecture 3 CDT 12 analysis of continuous beam by using a moment distribution method of analysis. So these are the lecture outcomes. So we'll see directly move to the problem. Let's analyze the continuous beam as shown in figure by moment distribution method. Draw the bending moment and shear force diagrams and draw the elastic curve also. So here I consider a simple problem. Two span continuous beam A, B, C. AB span is subjected to uniform distributed load and BC span is subjected to point load of 72 kilonewton, eccentric point load of 72 kilonewton is there. So uniform distributed load of 30 kilonewton meter is there. So if you, first step what we need to do, we need to observe the number of unknowns in the given structure. So if you observe, support A is a fixed support, support C is a fixed support, support B is a roller support. So we know at roller support theta B is unknown, theta is unknown, that is theta B is unknown. So fixed support theta is 0. Here also theta is also 0. So displacement is also 0 everywhere. Delta is 0 here, delta unless specifically mentioned anything thinking of support or anything. So delta values will be 0. So we can observe from this, we can observe only unknown is theta B is the unknown. So degree of indeterminacy, that is kinematic indeterminacy will be 1. Okay. So now we want to analyze by using moment distribution method of analysis. So for that, what we have to do is the first step of analysis, we have to calculate the fixed moments. We need to calculate first step 1. We have to calculate the fixed end moments. So we know this is a uniform distributed load. For uniform distributed load, the fixed moment can be calculated as from this formula WL square by 12. For eccentric point load, the fixed moment can be calculated as W A B square by L square and W A square B by L square. So this is also WL square by 12. From this formula, we know very well about these formulas. So from this formula, you substitute W value and L value. So this will be minus, this will be minus. AB will be minus, BC will be minus. BA as well as CB will be positive. Okay. So just calculate fixed moments, you're going to get minus MFAB is equal to minus 90, MFBA is equal to plus 90, MFBC is equal to minus 32, MFCB is equal to plus 64 kilonewton. So this is the step 1. So after that, in the step 2, we have to calculate the distribution factor. So we know distribution factor is member stiffness by joint stiffness. Member stiffness by joint stiffness. So we need to calculate. So we need to identify how many joints. So we have joint B, joint A, joint C. But at joint A, only one member is meeting. At joint C, only one member is meeting. So we have to calculate distribution factor for joint B, for BA as well as BC. So right, at joint B, we have to calculate member stiffness of BC. We need to calculate. Right. So if we know if the far end is fixed, the stiffness will be 4EI by I. But here I value for the AB member is 3I. You substitute 3I. L value 6. You're going to get stiffness K will be 2EI. Okay. For BC, I value 2I. L is equal to 6 meters. We calculate. So now you have to calculate the joint stiffness by adding member stiffness of B, stiffness of BA and stiffness of BC. You're going to get the joint stiffness 3.33. So now distribution factor for the BA member will be distribution factor for BA will be equal to stiffness of BA divided by joint stiffness. Stiffness of BA is 2EI by 3.33 EI. You will going to get distribution factor for BA member is 0.6. So similarly, distribution factor for BC also that is 1.33 EI divided by 3.33 EI. You solve this 0.6 and 0.4. So you can check like this. So summation of distribution factors in the joint must be equal to 1. So this condition you need to check. This is one of the check. Sum of distribution factors at the joint must be equal to. So after calculation of distribution factors, so we need to form the distribution table. This is the distribution table. In this distribution table, first we need to write the number of joints, A, B, C joint, as well as distribution factors we have to write. Distribution factor A and C is equal to what? A to B. Distribution factor of BA is just now we are calculated 0.6 that we need to write. We need to draw this table first. After that, the left side of the table, that is BA side, we need to write distribution factor. The distribution factor of BA is 0.6 that we need to write here. Distribution factor for the BC, we are calculating the 0.4 that you need to write here. So after that, the distribution factor. After that, this is fixed moments we need to write. Fixed moments we are calculating in step 1. MFAB is equal to minus 90, MFBA is equal to plus 90, MFBC is equal to minus 32, 64. So these values you have minus 90, plus 90, minus 32, 64 you have to write. Right. If you observe, at joint B, according to joint equilibrium equation, summation of moment of its joint must be equal to 0. If you observe, this is my plus 90 minus 32. There will be some unbalanced moment is there. Unbalanced moment is there. So that unbalanced moment we need to balance it. Okay. So we need to calculate the unbalanced moment. So plus 90 minus 32, that is plus 58. Plus 58 kilonewton meter unbalanced moment is there. So to balance this 58 kilonewton meter, we need to apply minus 58 additional moment of minus 58 kilonewton meter at the joint B. So because of the application of minus 58 kilonewton meter at joint B, so some of the moment will transfer to some of these. So here I am applying minus 58 kilonewton meter. So by applying minus 58 kilonewton meter, so some of the moment will transfer to BA member as well as some of the moment will transfer to the BC member. Okay, how it will transfer? It is based on its distribution factor. So how to calculate the how much amount of moment is transferred to BA member, how much moment of transfer to BC member? So how to calculate minus 58 multiplied 0.6? That is the distribution moment to the BA member. Minus 58 multiplied 0.4, that will be the distribution moment for the BC member. So minus 58 multiplied with 0.4, you're going to get minus 23.2. Minus 58 multiplied 0.6 minus 34.80. So that value is right. So we know that means we are additionally applying this moment. So we are additionally applying this moment for the BA member. So if we know according to carryover moment, carryover theorem, if you apply any moment by allowing rotation, half of the moment will going to develop at the far end also. So minus 34.8 into half end, and minus 17.4, minus 20, it will transfer to the far end. Minus 23.2 divided by 2, in the half will transfer to the far end. Now add all these moments, you're going to get the final. Now you check the joint equilibrium equation. It is equal to 0. That means if you add summation of moments at joint be equal to 0, just say it is 0. That means it is satisfying joint equilibrium equation. So we can conclude that these are the final end moments. So now MAB is equal to MAB is a minus 107.4. Now moment at B will be 55.2. Moment at C will be 52.4. So these are the final end moments. Thank you.